I believe almost everyone has heard about how much Taylor Swift has been flying. As a nuclear chemist, one might think, wow, she must get a lot of radiation exposure. Yard released a report stating that this woman has made about 170 flights since January 2023, spending about 16 days in the air, and that's not even while she was on tour. On average, her plane has been in the air for 80 minutes per flight, covering approximately 225 kilometers, which is roughly the distance from Cologne to just short over Heidelberg. Don't calculate the speed, the plane couldn't take off. Okay, strange numbers, whatever. So yes, she has a massive CO2 footprint, and whether the numbers are accurate or not, let's set that aside. We are in nuclear chemistry, and we are interested in how much radiation has she been exposed to. Why do you get radiation exposure during a flight? Up there's very little air shielding you. Hopefully that's clear. The sun bombards us not only with sunlight, but also with protons and alpha particles. These protons hit the very thin atmosphere and completely destroy the atoms. In technical terms, spallation reactions occur. So there's quite a bit going on up there. The spallation products then rush through the plane and through you, resulting in increased radiation exposure. There has been a great website where you could estimate the dose you'd receive from flying from point A to point B. Some flights, even if shorter, have higher radiation exposure than others. For example, flights over the poles are quite radiation intensive. So let's calculate how much radiation Taylor Swift will be exposed to on her The Eras Tour 2024. In November, she goes to Mexico City from, let's say, Nashville, Tennessee, USA, since she has a big penthouse there. Nashville to Mexico City, about 3 hours flight, equals 15 microsieverts. Mexico City to Buenos Aires, 8 hours of flight plus 40 microsieverts. Buenos Aires to Rio de Janeiro, plus 15 microsieverts. Rio de Janeiro to Sao Paulo, 0.6 hours of flight time, 1.8 microsieverts. Sao Paulo to Tokyo, 23 hours of flight, plus 184 microsieverts. Tokyo to Melbourne, 8 hours of flight, 50 microsieverts. Melbourne to Sydney, 0.8 hours of flight time, 2.5 microsieverts. Sydney to Singapore, 7.5 hours of flight, plus 37.5 microsieverts. Singapore to Paris, 13 hours of flight, plus 104 microsieverts. Paris to Stockholm, 2 hours of flight plus 6 microsieverts. Stockholm to Lisbon, 3.5 hours plus 10.5 microsieverts. Lisbon to Madrid, 0.6 hours of flight time, 1.8 microsieverts. Madrid to Lyon, 1 hour flight time plus 3 microsieverts. Lyon to Edinburgh, 1.5 hours plus 4.5 microsieverts. Edinburgh to Liverpool, half an hour of flight time plus 1.5 microsieverts. Liverpool to Cardiff, the same. Cardiff to London, still the same. London to Dublin, 1 hour flight time plus 3 microsieverts. Dublin to Amsterdam, 1 hour flight time plus 3 microsieverts. Amsterdam to Zurich, plus 3 microsieverts. Zurich to Milan, plus 1.5 microsieverts. Milan to Gelsenkirchen, plus 3 microsieverts, although Gelsenkirchen doesn't have an airport. Gelsenkirchen to Hamburg, plus 1.5 microsieverts. Hamburg to Munich, plus 1.5 microsieverts. Munich to Warsaw, plus 3 microsieverts. Warsaw to Vienna, plus 3 microsieverts. Vienna to London, 4.5 microsieverts. London to Nashville, 8.3 hours of flight time, plus 108 microsieverts. So in total, she would receive 614 microsieverts just from flying. I initially used an ordinary online flight dose calculator app and assumed 3 microsieverts an hour of flight time. Then I checked the literature and realized that was a bit too low for all flights within Europe, and everything under 3 hours I kept it at 3 microsieverts per hour of flight time. Flights longer than 3 hours were calculated at 5 microsieverts an hour of flight time due to higher altitude, and the transoceanic flights and the one over Eurasia were calculated with 8 microsieverts an hour. Is there a better way to calculate this? Absolutely. Now, are there standard values to indicate how significant 640 microsieverts is? Sure, an average person who might need to go to the hospital for a broken arm, eats normal food, and is not involved in nuclear chemistry and doesn't smoke, receives about 3 millisieverts a year, so 3,000. The law sets a limit of 6 millisieverts a year for flight personnel due to their work, assuming they spend about half of their 1,700 working hours per year in the air, which corresponds to 7 microsieverts per flight hour. The actual radiation exposure is likely close to this limit, otherwise this reference value would have not been chosen for flight personnel. Most of the radiation exposure during flight comes from protons and neutron radiation. Don't worry, even though it's neutron or proton radiation, the energy is way too high for you to become radioactive from it. They just pass right through you, smashing some molecules in the process. There's actually professional data for a flight, Singapore to Sydney. Flight time 6 hours 38 minutes, and they measured a dose of 15 microsieverts. Yes, this flight direction was reversed, but here we have a professional anchor point for the data from the online website that I used. So for short flights, it's still accurate, but as mentioned earlier, you can see in the documents that long-haul flights are significantly more radiation intensive, and indeed, there are other factors that make this 3 microsieverts an hour assumption a bit low. Well, what exactly is cosmic radiation? It's mostly protons and high-energy photons that hit the atmosphere. For example, a proton hits oxygen-16 and splits it into 3 protons, a neutron, a helium-3 and a beryllium-10, for example. This creates secondary protons and neutrons, and these neutrons can, for example, then further hit nitrogen-14, producing carbon-14, through a NP reaction. This is how cosmogenic nuclides like tritium, carbon-14, aluminium-26, chlorine-36, manganese-53 and nickel-59, as well as a bunch of gammas, neutrons, protons are formed, and you fly right through all of them when you are on the plane. Now I'm going to tell you a bit more about influencing factors of radiation dose when it comes to flights. Now we're going quite deep into the subjects. I hope you have a basic understanding of astronomy. First, the most obvious, altitude. The higher you fly, the more radiation you will get. I think I can just throw that out here. This is also quite intuitive since radiation comes from above. This graph shown is something that I think I need to explain since freedom units were chosen. The y-axis shows the effective dose rate and the x-axis represents altitude in flight levels. Flight level number 300 corresponds to an altitude of 30,000 feet. So the graph covers a range from 9,144 meters to a flight level of 390 or 11,887 meters. Thanks America for these freedom units. These secondary photons have an energy of 10 kiloelectronvolts to 1 gigaelectronvolt, and the secondary neutrons have maximum energies of 10 gigaelectronvolts. These are far away from being thermal, so N-gamma reactions will not occur that much. This stream of secondary particles results in the highest dose rate at altitudes of around 20 kilometers. Good things that most planes do not fly that high. Additionally, it's not only important how high you fly, but also what latitude you are on. The geomagnetic field, that is the Earth's magnetic field, is the most effective at shielding cosmic radiation in the regions near the equator at low altitudes. There, the fewest incoming particles are deflected vertically to the ground. When we talk about latitude, however, we refer not to the geographical latitudes relative to the geographical North and South Pole, but to the magnetic latitudes, which uses the magnetic North and South poles as references. This leads to an interesting phenomena, the so-called South Atlantic anomaly, a region where radiation exposure from cosmic rays is unusually high. Flights through these regions are avoided as much as possible. This is because, as I just mentioned, magnetic and geographical poles do not align perfectly, and this zone, the inner Van Allen belt, comes down to just 200 kilometers, compared to the typical 640 kilometers. The Van Allen belt describes a region with increased number of highly energetic particles trapped by the Earth's magnetic field, where more charged particles are closer to Earth's surface or atmosphere, more cosmic radiation is generated, leading to higher radiation exposure for people flying through it. And this is the South Atlantic anomaly. Another variable is the solar activity. The intensity of galactic radiation depends on the interplanetary magnetic field generated by the Sun, which varies with the 11-year solar activity cycle, from which solar radiation also results. There is a distinction between the geomagnetic and the interplanetary magnetic field. The geomagnetic field is mostly constant in strength, except after large coronal mass ejections. Now the interplanetary or solar magnetic field increases with strength, with the solar activity. Now here it gets interesting. One might think that the higher the solar activity, the radiation exposure would also be higher, right? However, that is exactly not the case. The stronger solar magnetic field actually provides better protection against the much larger galactic component of the cosmic radiation. Thus, radiation dose is lower during periods of higher solar activity. So we have learned something new today. So the radiation exposure Taylor Swift receives while flying during her tour is around 615 microsieverts, which is quite significant, but still far from being harmful to health. It pales in comparison to the 3000 microsieverts she would have normally received in a year. The calculation of radiation exposure during flights depends on many factors, such as flight altitude, flight route, proximity to the equators or the poles, and the solar activity. Taylor is also quite lucky that 2024 happens during a year of very high solar activity. Otherwise, her radiation exposure could have been way higher, by up to 50%. A special thanks goes to the Working Group of Analytics and Fundamental Nuclear Chemistry from Dr. Erik Strupp and the Division of Nuclear Chemistry at the University of Cologne, and to my Patreons. With that being said, thank you for your attention and goodbye!